Okay, let's continue where we left off. We looked at some properties of generating functions, and the motivation was to try and find the extinction probability of a branching process. So I'm now going to state the result, and then we'll use what we know about generating functions to prove it. So theorem, and this is Theorem 3 in your lecture notes. So let Zn be a branching process. And let G denote the generating function of the offspring distribution. Then the extinction probability which we'll denote by PE, which we defined earlier. So this is the limit as n goes to infinity of the probability that Zn equals 0. This extinction probability is given by the smallest solution x in the closed interval 0, 1 of the fixed point equation gx equals x. Okay, take the generating function of the offspring distribution, find a value x for which gx equals x. And okay, and we look at what the picture looks like, and so what the smallest solution looks like. And that's going to give us the extinction probability. Okay, and moreover, we can say something about the solution. The extinction probability is 1 if the mean of the offspring distribution is smaller than 1. We saw this already. If the mean number of offspring is smaller than 1, then extinction is guaranteed. And we will show that if the mean number of offspring is bigger than 1, then this extinction probability is strictly smaller than 1. It won't be 0. There'll still be a chance of becoming extinct. As long as it's possible to have 0 children, there's a possibility that the very first individual has 0 children, and so you become extinct. But there will be some positive probability, 1 minus PE, that the process survives forever, that it never goes extinct. Okay, and PE is given by the solution of this equation. So this is the statement of the theorem. And as usual, before we go on to the proof, you should take a few moments to make sure you fully understand the statement of the theorem. So given an offspring distribution, can you calculate what the extinction probability is, at least in principle, or can you calculate it numerically? Can you write a program in using your favorite software package to calculate this. Okay, so that's the theorem. There's a formal proof in the notes. I'm mainly going to do a proof by picture now, and also draw the picture to show you what the solution looks like. And why we went to all the trouble of looking at various properties of G. So I want to make this drawing fairly big so it's easy to read. Okay, so this is the line, the 45-degree line, X. And this is the square, 0, 1 by 0, 1 square. X is on the x-axis. And here is the generating function gx, which I want to draw. Which looks something like this. So this line up here is x. The curve down here is gx. And where they meet, this is the smallest solution in the interval 0, 1 of the equation gx equals x. And this solution is PE. There's always a solution at 1 because g of 1 is 1. So the line and the curve intersect at 1. Okay. G1 equals 1, we saw that. So there's always a solution at 1. And maybe that's the only solution. That could happen, and we'll come to that in a moment. But if not, if the curve looks like this, there's one more solution here. What cannot happen, and it doesn't matter for the statement of the theorem, but just to clarify things for ourselves, what cannot happen is this curve meets this line multiple times. It wiggles, it goes up, goes down, etc. And that follows from the convexity of G. If the function G is convex, a convex function can intersect a straight line in at most 2 points. Okay, there's a solution up here, 1. If there's another solution at PE, those are the only solutions. They cannot intersect more than 2 times. Okay, it's not so important that that G is increasing for this part anyway. But let's see why PE is the extinction probability. So we saw that the probability that Zn equals 0, probability that Zn equals 0 is the composition of G with itself, n minus 1 times, evaluated at 0. So let's evaluate that. So let's start with 0. What is G of 0? This is G of 0 here. Okay, so this point here is G of 0 because that's the function G. And typically it'll be above. It could be 0 if there's no probability of having 0 offspring, but as long as G of 0 is the probability that psi 1, 1 is 0, that you have no offspring. And in the interesting case, this is strictly positive. Otherwise, the process can never go extinct. So G of 0 is something positive here. Next, we want to calculate G of 0. How do we do that? So we've gone to g of 0 on the y-axis. So let's go to g of 0 on the x-axis. And we do that by going to this straight line and coming down here. So this is g of 0. Now, if you want to calculate g of 0, you are evaluating g at this point. So at this point, you are going up to the curve, and that happens here. And this point here is g of 0. And then to calculate g of 0, you then extend this back to the line. So this is your point on the x-axis of g of 0. And then you evaluate the curve at this point and keep going backwards and forwards. And you can see that you are getting close to this point here. So maybe I'll show what happens. Just maybe it's worth blowing up the curve and the line just up to that point. So here is the curve, g of x here, and this is the straight line, okay. The 45-degree line, which means somewhere there. Yeah, I can't draw it big enough to make the picture. Let me clear it and try again. Okay, so here is the function g, meeting it somewhere far away. So this is g of 0. Up here is g of 0. We go to this line and up to the curve. That gives us g of 0. And you can see that as you keep doing this repeatedly, you're going to come to the point where the line and the curve meet. So the limit as n goes to infinity of g of g, n minus 1 times or n times of 0 is going to take you to PE, the point where the line and the curve meet. Okay, so that's just a proof by picture of the theorem. There's a more formal proof in the notes, which I'm not going to go into. Good, so that's why it converges to this. Okay, and you can see that if there aren't more solutions, but you are always below this solution and you are getting closer and closer to the first solution if there are multiple solutions because you've started at 0. Now, okay, so that's the first part of the theorem. The second part said that the extinction probability is 1 if the mean offspring distribution is smaller than 1, and it's strictly smaller than 1 if the mean is bigger than 1. So let's prove that. And for that, we look at what happens at 1 to the line and to the curve. So again, let me blow up what happens here. So here is the line x, and here is the curve g of x. So this is the line x, and this is the curve g of x. The slope of the line is 1. Okay, the slope of the line x is 1. And the slope of the curve gx here is g prime of 1, or more precisely, the limit as u increases to 1 of g prime of u. But to keep it short and sweet, let me write g prime of 1. But this is the mean, and we saw that this is the mean of the random variable for which we are calculating the generating function. So this is the mean offspring distribution. And if it's bigger than 1, if the mean number of offspring is bigger than 1, the figure is exactly as I've drawn it. So this bit is steeper than the straight line, so the curve is below the line at 1. If the mean of the offspring distribution is smaller than 1, the curve lies above the line. Okay, and the curve is going somewhere here, and the line is going down to 0. And the only intersection between the curve and the line is here. There can't be any other intersections by convexity of G. So if the slope here is smaller than 1, then the curve always has to lie above the line and there are no other intersections. So the smallest solution of the equality is at x equals 1. There are no other solutions strictly smaller than 1. So here PE is 1. But if the curve lies below, then there is some solution PE which is smaller than 1, which could even be at 0, but typically it'll be strictly bigger than 0. So that's PE. Okay, so that completes the proof of the theorem. So that finishes our discussion of branching processes, and that's the main part of this section of the course. The motivation for looking at branching processes was to say something about the giant component of the Erdős-Rényi random graph. Okay, so back to connected components. Of Erdős-Rényi random graphs. Okay, so we describe connected components by saying start with a vertex and start exploring its neighborhood. Look at how many neighbors it has. This is some random variable with a Poisson distribution. Let me again. Okay, so we are looking at the Erdős-Rényi graph G n lambda over n. So the edge probability is lambda over n, and lambda bigger than 0 is fixed, doesn't depend on n. And we are looking at a sequence of such graphs as n goes to infinity. So we start at some vertex u, it has a random number of neighbors, and that's going to be a Poisson random variable with mean lambda, approximately. It's binomial with parameters n minus 1 and lambda over n, but approximately that's Poisson lambda. Okay, and think of these as the children of u. And now each of these children similarly has a look at all the neighbors of this child v. Then there are some random number of children. And maybe this is w, maybe w has no more children. This is x. X has children, some of them, so one of the children of x is the same as a child of v. This could happen, but if we just look at the children of each of them, they are all independent, they are not independent, but they are approximately independent Poisson random variables with the same parameter lambda. Because n is very big, there are a small number of children, the chance of something like this happening is very tiny early on. The neighborhoods of distinct nodes are going to be non-intersecting. The probability of an intersection is very small. So what you are seeing is you start with a node u, its neighbors, thought of as the children of U, are a Poisson number of, so it has Poisson lambda number of children. Each of those children again has a random number of children, maybe 0, maybe 1, etc. And you keep going exploring these neighborhoods. If lambda is smaller than 1, then what you have, the number of children is Poisson lambda. So if lambda is smaller than 1, then mean number of children is the mean of a Poisson lambda random variable. And we know that the parameter of a Poisson distribution is the same as its mean. So that is lambda. Okay. And so the mean number of children is smaller than 1. And we just saw that if you look at a branching process with a mean number of children smaller than 1, then that branching process goes extinct. Okay, so we have here a branching process with offspring distribution, which is Poisson lambda. N has disappeared. Nothing here depends on N. It's just something that depends on lambda. Okay, so we have, starting exploring the neighborhood from U, what we see looks like a branching process, and this branching process becomes extinct with probability 1. So it may take a long time to become extinct. Maybe there are 20 children or 100 children or 20 descendants or 100 or 10,000 before it becomes extinct, but eventually it becomes extinct. So as n goes to infinity, when you start from any vertex and explore its neighborhood, you are seeing a connected component whose size is of order 1. It's some constant, it's random, but it doesn't depend on n, it's some constant. So similarly, starting the exploration from each of the vertices. We claim that the largest connected component is of size log n. Where does the log n come from rather than order 1? It comes from the fact that we are doing this exploration starting from each vertex, and so we are taking the maximum of n different things. With a bit more care, you can show that the random variable, the size of this branching process, has exponentially decaying tails. And so the maximum of lots of these random variables is at most log n in size, if you take the maximum of n of them. Okay, so that's a very rough intuitive explanation for why component sizes are at most logarithmic in n if lambda is smaller than 1. If lambda is bigger than 1, then this branching process has non-zero probability of surviving forever. So if we start the exploration from some vertex, it has positive probability of extinction, so it might die out, and all you end up with is seeing a connected component of constant size, which doesn't depend on n. But with some probability, the branching process never dies out, meaning this exploration in principle goes on forever. Of course, it can't go on forever because there are only n nodes in total, and at some time, you will hit all of them. So at some time, the branching process approximation breaks down. Once this gets big, you will see many more of children being nodes you have already seen. The child of this vertex might be some vertex you've already seen, etc. So the branching process is no longer a good approximation, but it stays a good approximation until you get to some epsilon n vertices for a very small fraction epsilon. So that gives you some intuition that the approximation only breaks down once you reach components of size linear in n. And so you do have the largest connected component is of size linear in n. It's okay. So this is just a hand-waving explanation. We've not proved that there is a unique large cluster. Maybe there are multiple clusters of size linear in M. So that can't happen for reasons we won't go into. And also we didn't calculate what the size of the cluster is, which our theorem stated, but that's related to the extinction probability of this branching process. Okay, so those are some details which are in the notes. They are not so important. So we are looking at somewhat advanced topics related to random graphs at the moment. What is important is branching processes. They are useful for studying random graphs. And with that motivation, we've studied branching processes in a lot of detail. And you should make sure you understand definitions of branching processes, their properties, and the theorems we proved about extinction and non-extinction of branching processes. The connection to random graphs I've been quite vague on, and you don't have to understand them in detail. But I just wanted to say that what looks like a very remarkable property of random graphs, this sharp threshold for when the giant component emerges, has a simple intuitive explanation in terms of branching processes. And that connection is important. Okay, so that finishes our discussion of branching processes. It also finishes our discussion of the giant component, large connected components in random graphs. We have one last topic to study on random graphs, and that is full connectivity. So we want to ask, at what edge probability, for what values of edge probability does the random graph become fully connected? And that's something we'll see next time. Okay, so that finishes today's lecture.